Hello all and welcome to this next video as we continue our journey into looking at polynomials of degree 3 or higher. Today we'll be looking at cubic equations in their, I guess their general form, which as written there is a bracket x minus h all cubed plus k. So far, if we think about the whole course, we've done linear, we've done quadratics, hyperbolas, truncus, circles, square roots. Now it's time to meet, as I say, they're the granddaddy of them all for now, the cubic function. We will very briefly look at quartics as well. But we're starting with graphing cubic, and we're starting with this general form. Hopefully, as soon as you've seen it, you're like, oh, it's got the A, the H, the K. I know what to do with those. I've seen those before. There are transformations. Pardon me. There are transformations, and if that's the shape, then I can start to apply this, and that's where we're going to start. The thing to note is with cubic functions, as soon as we get away from them being in this general form, they start to get much more complex or harder. They aren't quite so easy. There's a whole lot more to them. But this is what the most basic cubic, y equals x cubed. It's got no x squared, no x term, no constant even. This is its most basic form. Now, you might notice this is a little bit weird. But why does it look this way? Okay. Now, if we think of a quadratic, and I'll come over here, y equals x squared, and then I'm going to put y equals x cubed over here. Let's think about our x, our resulting y, and for a x squared, a quadratic, if I put a negative x value in, because it's squared, it becomes positive. And then again, if I put a positive and then square it, it also becomes positive. So that's why we get that sort of shape of a quadratic. I'm putting in positives and I get a positive out. I'm putting in negative values, I get a positive out. Now, with a cubic, if I do that same sort of thing, think of x and y, and I put in a negative, well, a negative cubed is negative by negative by negative. That actually also still stays a negative. I put a positive in, it stays a positive. So that's where we get this idea that as I put positive in, well, it becomes positive, but as I put negative values in, it becomes negative, and it also becomes, the y values become greater quicker because it's a cubed instead of a squared. So if we put y cubed and x squared on the same graph, it's going to look like, I just need to adjust this one. Actually, I can use the middle one. If I put x squared on here, it's going to be higher, but it's going to be, my turning point's not very nice, not very round. Okay, it's going to be something like that. Okay, we need greater x values when we're greater than 1. We need greater x values to get to compared to an x cubed, because cube increases quicker. So that's why that shape is what it is. Now, the other thing to note, like a quadratic, we have a key sort of point on at least a standard form cubic. We have this point here. Now, this is called a point of inflection. Now, it's hard to see, and it's rarely ever drawn properly, but the gradient at that point is actually 0. The line comes, gets flatter, 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 and it technically just at that point right there, the gradient gets flat, it gets 0, and then it ramps back up. Okay, so when we draw our graphs now, and especially if we're zoomed out on a CAS or something like that, it might look something like that, but technically just at that point, the gradient is 0 when we're in this standard form. Right, so let's get on to how do we actually go about graphing these? How do we go about graphing these? Well, let's bring up Desmos quickly and have a look at a standard cubic. So I've set up sliders here for A, H, and K. I've left A as 1, so that's our dilation. If we remember, A is our dilation, H is our horizontal translation, and K is our vertical translation. That's what's happened in every single other relational function we've looked at to date. Let's see if that holds true. So let's start with H, horizontal translation at 0, and our key point there, that's our point of inflection if we watch that. As I increase H, shock horror, my graph translates to the right. As I make H negative, it comes down here. And the key thing to remember, like all those other functions, is we've actually got X minus H. So if I was putting negative 5 in there, it'll appear as X plus 5, but so we're inverting the sign. But we get that same pattern. As we change H, it translates the graph left or right. What happens with K? As I increase K, while the graph is translated upwards or along the y-axis in the positive direction, as it becomes negative, it's translated down, it becomes negative. So we have that. And then A, as I increase it, it's sort of hard to see, but that is stretching, that is dilating the graph. It's stretching every point. Can I label a point? I don't know how to do it on Desmos. No, I can't remember. But what is happening, especially if I start with a really small number, that graph is being stretched away from the x-axis. This curved line is being pulled up. So increase, increase, increase. And if we make A negative, it is that reflection. It flips the graph about the x-axis. It's flipped it upside down. And same thing, as I start to increase that negative, it's stretching, stretching, stretching. Stretches the graph away. And so if I can stretch, then I translate it across. I might translate it up. So my point of inflection we can see is at 2, 2. Well, let's maybe make it 2, 1, so we can see the impact H translated across 2. K is translated up 1. We've got A of 5, so it's actually really quite elongated vertically. So that's our transformation. So let's jump back. That's what all this says. Dilation, and then A also acts as a reflection if A is less than 0. So as soon as we make A negative, the whole thing gets reflected. H is our X translation, Y is our K is our Y translation, and we can see that change. If I started with X cubed, then made H 3, I've come across, and then as I add the K negative 2, I've also translated down. Right, so let's sketch. So just like everything else before, since we know this as a key point and it's written in this sort of form, we've got our H and K, is we want to identify where that key point is. In our case, it's our point of inflection. And from there, once we have that, we just need to get our intercepts, and that's it. So it's very, very similar to everything else we've done, is our key point, which is our point of inflection. And then 2, we need to get all intercepts as needed. So let's sketch the graph of f of x is equal to x plus 2 or q plus 1. Straight away, I can see h is negative 2 and k is 1. Remember, we switched the sign for h. So we get that. So my point of inflection is at negative 2, 1. So let's put that in. Negative 2, 1. Put it there. And then I just need to find my intercept. So let's do y-intercept. That's generally easier. We let x equal 0. So we get y is equal to 0 plus 2, or q plus 1 is equal to 2 cubed is 8 plus 1 is 9. Okay, 1, 2, 5. We're going to have to change our scale. Our y scale, we're going to call that 2, 4, 6, 8. That gives us enough room, but we'll leave x scale the same. So that was our y-intercept. Our x-intercept, we let y equal to 0. So we get 0 is equal to x plus 2 all cube plus 1, so negative 1 is equal to x plus 2 all cube. Now, how do I move the cube? Well, before, if we had a square, the inverse of the square was to take the square root. And technically with the square root, there's actually a little hidden 2 there. We just don't write it. If we don't see the 2, we assume it's a square root. Now we can do the same thing for a cube. We can actually take the cube root. So I can take cubed root of both sides, and that's going to cancel. So on the right hand side, the cube root and the cube cancel, so I'm left with x plus 2. Now the cube root of -1, that's asking, or cube root is asking, what is some number, okay, a, we'll call it, what is some number a where a times a times a is equal to -1? That's what the cube root is implying. And in this case, 1's easy because it's just going to be 1. So -1 by -1 is +1, but times by -1 again is -1. So we get -1. If we were asked for, say, the cubed root of 8, well, that's asking for what is some number a where a times a times a is equal to 8. Well, in that case, it's a is equal to 2. So that's all the adjustment we need to make for a cubed root. Here, because it's being multiplied by itself 3 times, we don't get that plus or minus effect like we do in square root. Okay? There can only be one sign. So if our answer inside the cubed root was negative, well, our answer needs to be negative. If it's positive, it needs to be positive. We don't have to actually worry about that plus or minus anymore. And we finally get x is equal to -3. So let's put in our key points here. Let's use maybe red. So that was our point of inflection, and that was at, and we label in coordinate form always, -2, -1. X-intercept was, what did we say, -3, 0, and our y-intercept up here was 0, 9. Okay, so how do you draw? What's the hints to actually draw this? Put a really tiny horizontal line through the point of inflection, and then from there, curl up to your key point. Put arrows on the end because we don't have any domain, so it technically needs to go on and on forever. And then same thing. And try and keep it roughly symmetrical about the point of inflection. When written in standard form, the graph is flipped, but that, I guess, symmetrical, you could say in some sense, or rotationally symmetric about the point of inflection. So that's one thing. Now, we don't actually, for the point of inflection, don't draw a dashed line through it. That would imply some asymptote. That's not actually the case. A bunch of people were making that mistake back when we were doing square roots. They were so used to truncus and hyperbolas that as soon as they got that key point for a square root graph, maybe starting there going off this way, they drew in a dashed line, That's a square root. Doesn't have an asymptote. Same with the cubic. Doesn't have an asymptote, so there shouldn't be any dashed lines floating about. Rightio, last thing. So that's all it is. Even if we had an A here, a 2, it's the exact same process. That 2 doesn't impact our point of inflection, so find that. Then the 2 will impact as we find our x and y intercepts. But once you have those 3 dots, it's just a matter of playing connect the dot. Rightio. Last thing is, because a cubic is a 1-to-1 function, it has an inverse. And when we take the inverse, when we switch the y and the x, just like sort of what we were doing when we're finding the x-intercept, we end up having to take the cubed root. Now the cubed root, we had the cube root of x, that is exact. We can also write that as x to the 1/3. So a lot of the time the inverse, or you'll be asked to plot a graph of something to the power of 1/3, that's just implying, oh, well, think of it as a cubic, but the inverse of the cubic. As we know from inverses, an inverse is just the original function reflected about y equals x. So there's a lot going on in that graph, but match the colors though. The inverse is the red line. So if we think about the inverse, starts here, goes up that way, comes down this way. So Again, the inverse of a quadratic is a square root. So if we think back to our quadratics, because we've spent so much time doing those, it's a great point of reference. Okay. The inverse of a quadratic was a square root. And we know it looks like that. And we had to restrict the domain of the quadratic because it wasn't naturally one-to-one. Now with the cubic, because we avoid that plus or minus scenario, and it's a one-to-one function, we can plot the whole thing. We don't need to restrict the domain. So the way way I think about it is, if I ever see this having to plot some form of a cubed root graph, I think it's sort of like a doubled up square root. It still has its h and k values, wherever that may be. In this case, it's just 0, 0. There's some sort of square root coming out that way, but there's also coming out this way. And it's not technically a square root because it's cubed root, but that's the way I think of it, is it's that sort of double up shape, and that can avoid confusion. So our very last slide, 4 minutes left, is sketch the graph of y equals x minus 1 to the power of 1/3 minus 2. So I think we need to recognize is, pardon me, is that it is a cube root. So we can still get our h value. So h is 1, k is -2. So my point of inflection is at 1, -2. So there, 1, -2. And then I just need to find the x and y intercepts. Now, like I said, it is going to be something up that way and something out that way. So we do know there is going to be an x-intercept. We do know there's going to be a y-intercept. So let's find what those are. So y-intercept, we let x equal 0. We get y is equal to -1 to 1/3 minus 2. The cubed root of -1 is just -1 minus 2, so that gives me -3. So that is 0, -3 is my key point there. And then my x-intercept at y equals 0, so we get 0 is equal to x minus 1 to the 1/3 minus 2. So we get 2 is equal to x minus 1 to the 1/3. Now, how do we move that 1/3? What's the opposite of a cubed root? Well, that would be the same as taking the whole thing and cubing it. That will cancel. So we get 8 is equal to x minus 1, so x is equal to 9. And that makes sense because it turns out that this is the inverse of this function that we did back here. It's flipped all the points. So we get, actually, yeah, it's flipped all the points. So 9, 1, 2, 7. I don't have enough space. So let's change our scale again. 2, 4, 10. So we're at 9. So that was 9, 0. Here was at 1, -2. Put a vertical line through it. Oh, that's also terrible. Okay. That's not the greatest. You want to make sure there's some curvature to it. Let's do that. There we go. That's better. Okay. You don't want to just draw a straight line. There needs to be some curvature to the graph. So that is our graph of f of x. And that's it. If you have any questions, put them below in Google Classroom or send me an email or ask in class. Have a good day. Yeah, that's it.